All right, so we're going to talk about line integrals. Okay, so the theory behind line integral, what in the world a line integral actually is let's suppose I have a nice curve, kind of like this. Okay, so I have an initial point. Let's say this is P naught all the way to here. Okay, so what I'm going to do is instead of taking the integral from A to B and just finding the shaded area underneath the curve, what we're going to do is going to find the integral with respect to this line or this curve itself. Okay, so here's our curve C, and how we're going to do this is we're going to make individual points, like from here to here. We're just going to make points on this actual curve, like that. So the whole point is this P sub n, right? So how this is going to process is, well, I'm going to find the length of this part of this curve. And the nice thing is, if I transform this down, this becomes just a straight line, right, each of the curvature. Like if I just straighten out in a flat line, and that's what we're going to find in what's called a line integral. So now we're going to find the arc length, if you want to call it, of a curve. The problem is, because we're valuing integral at a curve, it's called a line integral. Okay. So again, once we add up all of these individual lengths together, hence called the Riemann sum, we get something called a line integral. Okay. Now this line integral is very familiar to, if you remember back in geometry, the arc length of a curve, and you'll see that in a little bit. Okay. So if f is defined to be a smooth curve, so meaning no, right, it's actually continuous, given by the equation x equals x of t, so in terms of t itself, so x and y is in terms of t, and then following f along a curve C, then this is going to be our line integral, right? So where this point right here is the individual points on this curve, and this is the arc length, or the length of the curve. Okay? So we can convert this to be the integral over a curve to from A to B of our function with respect to t times the arc length of the curve, right, in respect to dt. Okay. So the thing is, we have to transpose our parametric with respect to t. So x has to be in terms of t, and y has to be in terms of t, if we have that. You'll see in a little bit if it's in terms of x and y, it gets a little easier to do that as well. Okay. So let's try this example out. How do we find now line integrals over a curve? So we're going to find the line integral of this function, ds, ds, where c is the upper half of the unit circle, x squared plus y squared equals 1. Okay, so given this curve right here, we want to integrate this function over this curve. And that's what makes it different than everything else we have done so far, because this curvature now is not a region, but just a length, one little sliver of the entire thing. So this is our curve C. Okay. Now it's the upper half, so it's going to be greater than or equal to 1, right? So it's the upper half, so nothing lower than that. So it's just going to be the half circle itself. Okay. Now, nice thing is we've got to transpose it, right? Parametric equations. So whenever you have x squared, y squared, you always go to polar coordinates. So will x be the same as we did before, r cosine t, and let y equal r sine t. Okay. Now all this is going to go from, is just 1. It's the radius, so it's just going to be length of 1. So it's just going to be x equals cosine t and y equals sine t. Okay. But we got to figure out bounds. So right now we have this curvature of this portion here, ds, which now becomes some curve evaluated with cosines and sines plus cosine squared t times sine, and then the square root of all of this. All right, so now we got to figure out what the square root is in here. This is going to be just a derivative squared and a derivative squared. So since r is just 1, so derivative cosine just going to be sine squared, it's going to be positive. This is also going to be positive. It's just going to be opposite. And this is what the nice thing about being polar coordinates. Sine squared plus cosine squared just equals 1. So all of that just goes away. Okay. All right, so that's gone. Now, again, if you're wondering, well, what if there's some r over here? Now, remember, it's not a double integral. If it was a double integral, I would have to put r over here for polar coordinates. It's only a single integration. It's only from a to b in this case. Okay. So, and notice there's no r's involved, so therefore our bounds are probably looking like theta. So this is going away, so now let's figure out what the c is going to be. Okay. All right, so we have our radius going to be 1, and now we want a theta. So for polar coordinates, it goes from 0 to pi. And there is our bounds. So from 0 to pi, and this now becomes 1. So we're just going to be integrating 2 plus cosine squared t sine t d theta. Or sorry, dt. All right, so now we just integrate with respect to t. So that's just going to be 2t. This one you could just use substitution. Let u equal cosine t, so therefore du is going to be minus sine t, so we minus du is equal to sine t dt. And there we go. That's what we're looking for. Okay. So this integration becomes 2t from here. The minus becomes a minus here. U squared, so just in case you're going to be u squared, that becomes cosine to the third over 3, evaluated at 0 and pi. Okay. So now we just plug it in and we'll see what we get. So plugging in pi, we get 2 pi here, minus cosine of pi is negative 1 to the third power is negative. Negative gets you a positive 1/3 on this side. Minus, and now I just evaluate 0. That goes away. Cosine of 0 is 1, so we get that. So we get 2 pi plus 2 over 3 as our answer. Okay. Now, an alternative to finding line integrals instead of having to parameterize everything in respect to t is use the easiest of the ones, is just keep it the same in terms of x and y. Okay. So for example, if we want to find the line integral just by using respect to x and y, which is, the easiest of the two to do, we don't have to convert it to a t-value or anything else. This is what's called a line integral with respect to the arc length. So this is given by the terms x equals x of t, y equals y of t, and then we just take the derivative of each one. So dx is x prime, and dy is y prime respectively. So we do the integral of respect to just x itself and y itself, and we just add the results together. Or essentially, you just pop that on top of here, so it just gets one long integral, which is nice. Okay. And our bounds are going to be either x or y, and vice versa. So how will this work out? Okay. Now, there's a problem when it comes to this type of situations. Because we're not parameterizing it, and our bounds is going to be not parameter in terms of t, same thing applies here is, okay, what's our bounds going to be? Because now we have x and y, respectively. So to do so, this is the one thing we do have to do instead of parameterizing, is find the vector representation of what we're doing. Okay. So to find the vector representation of it is, given a point, so initial point and a terminal point, we can create a vector representation just by simply using this equation here. Okay. So we're actually going to use this in a little bit. All right. So after all of that, how do we use that information to break it down? So let's suppose we want to find the line integral of y squared dx plus x dy. Now, here's a fun little fact. Whenever you have looking for this kind of stuff, you want to look for the line integral of this function, and notice it has dx and dy. That's when you know we're going to be doing this kind of stuff. Okay. right? So not this, but actually this. Okay. Okay. So now that we have that hint, we have A and B. So the C is a line segment from -5, 3 to 0, 2. All right. So let's just graph what's going on here. Okay. So our first point is 0, 2, which is right here. And the next point is -5, -3. So 1, 2, 3, 4, 5, -3. So it's a line segment. So that is our C. We'll call that C1 since we have A and B. That's our curve C1. So it's a straight line. Okay. Now, because everything's in terms of X and Y, that means we have to figure out what's going to be our X representation and our Y representation. Okay. Now, that's where this comes into play, this vector representation. Okay. So we're going to find the vector representation given our initial and terminal point. So it's just going to be 1 minus t times our initial point, and that's going to be in vector format, so it'll be looking like this. That. And then plus t times the terminal point, which is there, like that. Okay. So distributing the -5 and then adding 0t gives us the first part is going to be -5 plus 5t. And then we do the same thing for the other component. So distributing -3 and then adding 2t to it gives us -3, and this negative makes it positive. 3t plus 2t gives me 5t, like that. So that's our vector r with respect to t. Okay. So that means my x component is going to be -5 plus 5t, and my y component is going to be -3 plus 5t. All right, so now according to my equation, I need to find both the derivatives, the partial derivatives, with respect to x and y. So I have to find dx and dy. So I just do with respect to t in each case. So with respect to t just gives me 5. With respect to t also gives me 5. Okay. So according to my formula, we'll figure out the bounds in a little bit. It's going to be y squared. So where's y? -3 plus 5t squared dx, which is just 5 at, plus the other part, x, which is just going to be -5 plus 5t times dy, which is again 5 dt. Okay. Now we got to figure out the bounds. So because everything is in terms of t, we have to find the bounds with respect to t. So where does t go to from one to the other? Okay. Now this goes up to here, these 2 points right here. So I need to figure out, I'll write this down, this is -5, -3, and this is 0, 2. So what t value will give me -5, -3 in here, and what t value will give me 0 and 2 respectively, there and there. So if I go here, you notice I have -5 and -3 already there. So it looks like if I plug in 0 in for t, that works. So it looks like that's the lowest one t can possibly be to hit this point. And now what do I have to plug into t to get you that point? And it's easy, right? I'm doing it the hard way, solve for it. So set x equals 0, set y equal 2, and just solve for t. But, algebraically and geometrically, isn't that hard to realize it, right? So in order to get x to be 0, t has to equal 1. And if t equals 1, that also makes it true, right? We get plus 2. So boundary is from 0 to 1. So this is from 0 to 1. Okay. All right, so now I just distribute this and unfoil this and make it a little easier to look at. So now it becomes integral from 0 to 1. And after foiling this and distributing, and then again distributing and collecting everything like terms, I get this for my unintegrated part. Like that. And now notice now this integral is much easier to deal with, right, than we actually did earlier with the parameterizations and all that fun stuff. So it's a pretty straightforward integral. 125 to the third minus 125 t squared over 2 plus 20t. And now again, this is evaluated at 0 and 1. Good thing is you plug in 0 for t, that all goes away, so the answer is just whenever you plug in 1 in for t. So this gives you 1 over 25 over 3 minus 125 over 2 plus 20. And I get approximately this as the answer. Okay. Okay. Now let's try part B. Now B says, oh, look at, we have the same points. Okay, so same points. However, now C is the arc of the parabola from x equals 4 minus y squared from this point to that point. So in fact, it kind of looks like this. So what is this going to look like? Make it black so you can see the difference. So we know it touches these points. So what does the graph kind of look like? So if I set x equals 0, so when x equals 0, y equals 4, or sorry, y equals 2, so it's that point. So when y is 0, x equals 4, so 1, 2, 3, 4. So it touches this point. So it curves like that. So that's going to be my C2. Okay. So now this is the curve we're going to be doing our integral of. So we want to find the line integral of C2 over this function there. Okay. Now, unlike the other one, where we had to find the vector, right? This one we're given. So we're going to use our parameterization of just y equaling y, and our parameter x is equal to 4 minus y squared, because it's always already in terms of x and y. So we don't have to convert it to any t values itself. Okay. Now again, the reason why we chose this one is because it's a literally line segment, so we have to find the vector. But if we're given an equation, we'll just use the equation, the easiest parameterization to do so. Right, you can use polar, but why make life harder for yourself if you don't have to do? Polar would have worked perfectly fine as well, but it would have been more messier to do so. So we'll just do the simplest one, right? It's always in terms of x and y already. Okay. All right, so we got our parameterizations. So now we just take the derivative with respect to each one. So this is going to be the derivative of that, just going to be 1 dy. Derivative of this is going to be what? Ooh, interesting, huh? So remember, here we took the derivative with respect to t, right, of dx. This one we're going to do with respect to y, so it'll be negative 2y dy, because that's our parameterization. That's our independent one we're going to be dealing with, which means our integral is going to only be in terms of y, not t. I know, a little tricky, right? A little confusing when it comes to that. Because remember, we're not taking the derivative with respect to x, we're only doing one term. And it's the reason why you just respect to t here. This one we're going to respect to y only, because that's going to be our independent variable. Okay. All right, so now we got everything we need. So we'll figure out our bounds in a little bit. So just y squared, so that's just going to be y squared times dx. So dx was minus 2y dy plus x, so all of this, times dy, which is just dy, 1 dy, right? Okay. So now let's figure out bounds. Now remember, everything's in terms of y, not t, right, in terms of y. So if I go up here, what's my y bounded from? Well, y goes from here to there, right, because this is the y components. So it goes from literally -3 to 2. There we go. Because if I plug in both of them here, we get exactly those points. Okay, so simplifying this again just a little bit. So this becomes the integral from -3 to 2. Distribute this using -2y to the third dy plus this just itself. I'll evaluate it now. Just put this on the outside. dy. All right, integrating this, y to the fourth plus 4y minus y to the third over 3. Evaluate it at -3 and 2. Okay. So when you plug in each one respectively and then you subtract, I get approximately 40.83. Now, if you're kind of confused, I'm glad you are, because this is just a, why don't they agree with each other? Right? There was curve, we're going to the same spot, that point to that point. This was just a straight line there. This was a curve to get there. But, you know, which one's true? And that's the interesting part. They're actually technically both correct, because a line integral is only represented as the curve you pick it and the actual points, so the endpoints. So just because you have the same endpoints, the type of curve you get would give you a different integral. And that's kind of good and kind of bad, right? The drawback is, well, all right, well, depending on the curve I get, I can get there a different type of way, you know, which is the most optimal way or which is something that's more useful for our cases. And we'll talk about that later on, but for now, we'll just say, you know, the way you parameterize x and y does affect what the answer is going to be, right? Because it depends on the curve to get there. Okay? Now, before we go a little further, let's talk about line integrals in space, right? So this is just 2 dimensions. So in space is 3 dimensions. It's the exact same situation. We have x, y, and z now z. And then same thing, this is going to be the arc length. And we just pop that in the end because now we have x, y, and z itself. So the nice thing is we use the same equation either way. Okay. So let's try an example before we go into 3 regions. So let's evaluate the line integral of this curve of y sine z ds with when the curve C is the equations x equals cosine t, y equals sine t, and z equals t. So they already parameterized, or they already told us what our portion is going to be, which means our curve C has to be in terms of respect to t, right? Okay. Now, they already give us this, so I'll just rewrite it here. So x is cosine t, y is sine t, and then z is just t. Okay, so according to our equation, just the same as a 2-dimensional one, I'm going to take the derivative of each one with respect to t itself. So this is just going to be negative sine, positive cosine, and this is just 1, right, dt dt. Okay, so, and the nice thing they told me are bounds, so from 0 to 2 pi. So everything's nicely set up. So y is, in this case, sine t times sine evaluated z, which is just t, which is nice. So it's just sine times sine ds. So our ds is going to be the square root of all this, right? So the sine squared t plus cosine squared t times 1 squared, it was just 1 dt. Now again, this is nice. This is just 1. right? So 1 plus 1 is 2. So this ends up being the square root of 2, so I'll just put this on the outside. So the integral is much nicer to look at. So again, just a quick little note. Integral of sine squared is just going to equal to 1/2 u minus 1/4 sine of 2u. So I'm going to use that property right here. So this is going to be the square root of 2 times, and then just t, so it'll be 1/2 t minus 1/4 sine of 2t, all evaluated at 0 and 2 pi. So plugging in 2 pi and 0. Plugging in 2 pi just gives me pi. Sine of 4 pi is 0. And on this side, plug in 0, you get 0. Sine of 0 is also 0. So we just get pi times radical 2. So what about curves in 3 dimensions? Or in this case, points. And we have to figure out those line segments in 3 dimensions, since this was already pretty much set up for us. So let's evaluate the line integral of the curve from x, d, y, all this fun stuff for c. Okay, now it's made up of 2 line segments. That's going to be key. C1 is the points from 2, 0, 0 to 3, 4, 5, and C2 is from the points 3, 4, 5 to 3, 4, 0. Okay. Now, what this means is we want the entire curve, right? So I'm just going to, an arbitrary curve. Let's say we have like this happening. If this is like my C1 and C2, for instance. So because we want the entire curve put together, I'm first going to find this line integral, evaluate that at that integration, and then again over here. And then I'm just going to put them together by adding them. So in other words, the entire curve itself is equal to the union of both line integrals, or in this case, the line segments put together. Okay. So that's what we're going to do. So we're going to separate this into C1 and C2, do each one individually, and at the very end, add up the both results to give us the whole curve itself, right? Integration over the entire 2 line segments. So for now, we're going to be going from here to there. Okay. And again, since we have points, and we're in 3 dimensions, same thing applies. So this is a t. Right, there's our vector. And it's in 3 dimensions, we're just going to add, right? So vectors could be in 2 and 3, so we're just going to add it there. So first curve is going from 2, 0, 0 to 3, 4, 5. So our vector, with respect to t, is going to be 1 minus t times our vector of 2, 0, 0, plus t times the vector 3, 4, 5. All right, so what does this give us? So 2 times this is going to be 2. 2 times is negative 2t plus 3t is going to be t. 0 times anything is 0, so that's just going to be 4t. And again, 0 times anything is 0 plus 5t. So there's our vector representation there. So this is our x, y, and z. Okay. All right, so now we find dx with respect to t. So that's just going to be 1. dy, oh, I'll put dt, 4. And then finally dz, which is 5. All right, so now we're going to take the integral of this curve going from y dx, so y is 4t, so 4t times dx, which is just dt, plus z, so 5t times dy, which is 4 dt, plus x, which is 2 plus t times dz, which is 5 dt. Okay. Now we're going to figure out bounds. Now everything in terms of x, in terms of t. So I know t is going to be from something to something. Okay. So what does t have to equal to make the first point 2, 0, 0? And again, you can just plug it in, right? So if 2 has to equal x, so 2 is equal to 2 plus t, and you can solve for t, that's just going to give you 0. Same thing applies here, right? 0 has to equal 4t, so that's not that bad. So it goes from 0. And with the highest point, ready? So again, you could just go solve it. You can just look right this one or this one. So 5 must equal 5t, so t has to equal 1. And the same thing applies, right? So 3 has to equal 2 plus t, t has to equal 1. So this goes from 0 to 1. Okay. And then we just take the integral. So I'm going to slowly break this down. Again, right, distributing and multiplying. So like, for example, here, this gives me 20 t squared. Distributing here, this gives me 10 plus 5t. And then putting everything together itself. Well, actually, this is just a t. Sorry. This is dx. Dx, this is just 4t. And this is just 5. Yeah, okay. So that gives me all of this. Let's see. Integral from that. And that gives me, let's see what we get. So 29t plus 10. So notice the integral is really nice to do. Just as a setup is the hard part. So 29t squared over 2 plus 10t, evaluate at 0 and 1. And again, 0 just doesn't do anything, so just 1. So 29 over 2 plus 10 gives me 24.5. And now, we do the exact same thing now, but except along the other curve. And the other curve goes from the end point of here. So it goes from 3, 4, 5 to 3, 4, 0. Okay. So therefore, we're going to have a new vector representation. Okay. And again, distributing this 3 and then adding 3. Notice the 3's end up canceling. We'll just get 3. Notice again the 4's end up canceling with the t, so we just get 4. And now for the 5's, it's plus 0, so it's just going to be 5 minus 5t for the z. So this is going to be x, y, and z. Which makes it much easier because now the derivative is just going to be 0 dt. For y, it's also 0 dt. And then for z, it's just going to be negative 5. And again, same thing. So since we're on those portions of it, so we could just go from t itself. So how do we go from here to here? Notice just 0. The only equation we have is here to here. To what? Well, if we plug in 1, I get 0. So the only term I can use here is right here. Everything else is consistent, constant, right? It doesn't go anywhere. It's only with respect to the z component is going up. Or in this case, back down to 0. So we go the integral from 0 to 1. And then we go back up here. Y times dx, which is going to be 0, z times dy, which is also going to be 0, x times dz. And that's kind of nice. You can't get any easier of an integral. So integrating this gives me that. So now the entire curve, or the entire C curve, from the first line to the second line is going to be the summation, or the sum of both of them. So it'll be 24.5 minus 15, which is going to be 9.5. And there we go. And that's our complete line integral of this function over these two line segments. All right. Now, what can we do for lines? We can do for vectors. Now, vectors themselves could be a little different, or vector fields even worse, right? Because vector fields are just components and curves. So how do we find the line integral of a vector field? Because, you know, a vector field is just a field of stuff, vectors going on, and showing you what the vectors are curving to, right? Where the flow is going towards, okay? So when it comes to vectors and integrating over vector fields, we talk about the same amount of thing. However, we're going to talk about the amount of work it takes to move an object from point A to point B. That's what a line integral represents to a vector field, how much work is being done to go from one point to the other point. Okay? So, again, a little theory to see what's going on. So, let's suppose I have this curve from P naught to point Pn, right, of all these individual points. And let's say I pick this 2 points right here. Okay. Now, we can find the tangent line, we can do all that fun stuff itself. Now, when it comes to vector fields, right, the vector field is first we have to find the tangent line, because that's what represents our vector fields. Okay, so let's suppose this is our tangent line. And now on this tangent line, we pick a couple points. Now, on these couple points, we can do, like, for example, this point here, we can do a lot of stuff going on, right? We can find a unit tangent vector, call that t, which is called the unit tangent vector, right? Way back in the day, we were able to do that. And we can find a force that's being applied to it, call that F. Okay. Now, force is what's being pushed down on it to move it, from one way and then right. So, like, if you flick something on the surface, there's force being pushed down to stop it, right? Same thing applies in this portion here. Okay. So the work to go from one point to this point, or throughout this entire curve, again, is a summation, right? So go from here to here, then there to there, and so forth. So it's a summation of points, or summation of work put together. But an individual point itself, we'll say. So the work being done is equal to the force, that's like being a resistance, which is going to be our function itself, times d, where d is the displacement of the vector, meaning how far it goes from there to there. Okay? So if we take the sum of all of these forces and all that fun stuff, so if you take the sum of the forces times the tangent vectors, because it tells you how much we're going this way, and then we do this. So this is how much each individual force of the function itself going from one to the other. Our tangent unit vector is how much we're going in that direction. And the change of s is how much we're going from all the way out the curve, right? The length of the entire curve. This applies, it gives us the work, which is what we want, of the integral of this curve of these things multiplied together, or the dot product of the f and t times the delta s. Okay? And that is what represents a line integral over a vector field. It's the amount of work. Or, a little easier just in terms of just one variable instead of just having to find the unit tangent vector, is this. So let F be a continuous vector field defined on a smooth curve C, given that the vector function R of t from A to B, then the line integral of F along C is given by this, where the vector itself is in terms of R and t, so you have to plug it in first, and we'll take the derivative of R as well. So given the vector function R and some F continuous vector field, that's when we find the line integral of it. So let's try an example so you can see how this looks in let's say 2 dimensions for now. Okay, so find the work done by the force field where F is equal to x squared I minus xyj, moving along the curve R of t. So they give us the parameter automatically, right? So everything's given to us. We don't have to find it, anything like that. Okay, so we're given this. So we got to do a couple things. First thing, we define the derivative with respect to t of R of t. So we'll just do that quickly. So derivative of cosine is going to be negative sine. Derivative of sine is cosine. Okay, that was easy. Next step is we're going to plug in R of t into F. So this is x squared, so it'll be cosine squared minus the multiplication of x and y. So minus cosine t sine t, the j component. Okay, so now our integral is the dot product of this and this So if we do dot product this and this, will be this times this plus that times that. So this times this gives me negative sine of t cosine square t. And this times this, so minus cosine square t sine t dt. Now notice these are the same. So there are two of them. And the nice thing is they even give us our bounds. So the curvature is just going from 0 to pi over 2. So again, this is just a quick u substitution. Let u equal cosine t, so then du is just equal to negative sine t du. So divide over the negative, so negative, negative, make it positive. So this ends up being integral of u squared, so just u to the third over 3. So this ends up being positive 2 on the outside. And we have cosine cubed of t over 3 evaluated at 0 and pi over 2. All right, so what do we get here? So we have 2 times, plug it in, so cosine of pi over 2 is 0, so that's just gone, minus cosine of 0 is 1, so just 1/3. So this just gives me negative 2/3. All right, so now let's try one where it's not given to us. The RT is not given to us. Well, kind of given to us, let's just say, but not in the sense of just it tells you it's RT. So find the line integral of the curve from where f, our vector field, is equal to this. And our curve is given by parameterizations of x equaling t, y equaling t squared, and z equaling t to the third. So remember, this is actually our r of t right here. So in the equations above, that's our r of t. Okay. So that means first we got to find r prime of t. And I'll put it in the same framework we did above. So derivative respect to t is 1, derivative respect to t is 2t, and then 3t. So that's our r of t. So then therefore f, our vector field, and a parameterization vector. So we just plug in each one of these where it's supposed to be. So x times y, so this times this is just to the third. Y times z to the fifth. And then z times x to the fourth. Okay, so now our integral is, again, the dot product of these two. So that times that, that times that, and then that times that. Oh, squared, right? Yeah, let's do the 6 dt. Okay, putting this together. And look at that. Nice integral. Doesn't even matter, we care about the bounds, right? That's a nice integral we're about to do. All right, now finally the bounds of integration. Okay, so where does t go to get this kind of stuff? Okay. All right, so how to find t in our boundary integrations? Let's go back to what we have. So we have this vector field, and it's in terms of these components, and our vector function is right here. Okay. So if I plug in 0, I get 1, 0, 0, which is the same process we have above. So therefore, t has to go from 0. And if I plug in 1, I get 1, 2, 3, which is the same process we would have in that portion. So that goes to 1 itself. So t goes from 0 to 1. So we have the integral from 0 to 1 of this nice process. Okay, integrating this. Oh, the integration's off. There we go. All right, 0 gun goes away. So we just plug in 1, so it'll just be 1/4 plus 5/7, and I get about 0.96. There we go.